This is video 9B using NRF24L01 devices for multiple nodes on STM32 MicroPython and the BlackPill. The code for this video is at the GitHub site. The information presented in these videos on MicroPython should work as well on any STM32F4 board. All code examples have pin definitions at the beginning of the file to allow the programmer to alter as needed. As this channel covers multiple microcontroller solutions over time, please subscribe to stay informed and click like as that really helps. In this video, we continue to use our STM32 BlackPill microcontroller on the car baseboard with an external NRF24L01 board to perform 2.4G wireless communication. We will use 3 sets of populated car baseboard. The baseboard includes an NRF24 port in the lower left-hand corner. The port means you can plug in the device and no other wiring is required. We will plug in 2 device boards with a PCB trace antenna and 1 board with an SMA antenna. The picture shows the 3 sets of boards and their names. Looking at left-hand information boxes, node 1 and node 2, each use their TX pipe to send data to main 0. They await an acknowledgement message on the RX pipe. Otherwise, they will retransmit. Looking at the right-hand information box, main 0 receives the transmitted data via the RX pipe and responds with a custom acknowledgement message using the TX pipe to node 1 or node 2. Let's restate the functionality for each microcontroller. The main functions are that main 0 waits to receive data and sends an acknowledgement. For the remote nodes, node 1 sends data and verifies the acknowledgement. On error, it retransmits. The same for node 2. Since we understand the wireless connections, let's deploy the MicroPython software. From GitHub, download the MicroPython files. Next, connect the BlackPill to your desktop and drag the files to the USB drive for each board as they open. The driver file should already be on the BlackPill from video 9. Each microcontroller could operate autonomously, but let's invoke the programs manually to see the sequence. Open TerraTerm and connect to main 0. Type the program name you deployed and follow the instructions by pressing the button. Open TerraTerm terminal and connect to it. Type the program name that you deployed and follow the instructions by pressing the button. Now, open bb_machine_radio_node1.py in Thony. Let's look at the code. The program set up for NRF24 the same as in video 9, except here we set the payload size to 32. By the way, for NRF24L01 the max payload size is 32 bytes. Additionally, our driver requires that it be the same fixed width for sends and receives. For example, in video 9 we set the payload size to 10 bytes. And so the send was 10 bytes and the response was 10 bytes. Let's click the green run icon. The program waits for you to press the user button. As you do, it transmits the 32-byte message to main 0. Alright, we already have main 0 running, so let's press the button on node 1. Okay, we can see that it sent the message 1 with the date, the time, and a floating point value and a random digital integer. The main computer responded with 1 OK. In other words, it read that this was node 1 and responded. You can see that it's a 32-byte response. This node 1 computer verified that it was OK. Let's send it again. Alright, slightly faster this time, around 200 milliseconds. That's comparable times for this system. Let's try node 2. Here we're clicking on the user button for node 2. You see it builds a message and sends it to the main 0 computer. Here we are looking at the main 0 server, and the messages it prints when node 1 sends to it. And now we'll watch as node 2 sends messages. The difference being the message mentions node 1 from the node 1 computer and node 2 and the node 2 computer. The main computer must parse that message and respond back to the right computer. Now that we know it works, let's look at the code. This is the code for node 1. You'll see that it's very similar to the code that we used in the first video 9. The only difference is that the payload size is set to 32, in other words 32 bytes. In video 9, we set the payload size to 10 bytes. And that meant that it needed to send 10 bytes and it needed to receive 10 bytes. As we saw in this example, it sent 32 bytes and it received 32 bytes. We also set retries to 3. We'll explain that in a minute. Okay, as I mentioned before, the setup for the radio is the same as before. For the node 1, we're setting the OpenTX pipe for main 0 because we want to send data to main 0. And any responses we want to receive on the receive pipe 1 using our address, which in this case is node 1. Then we have a set of routines that we use to build the message. We have the verifier routine that we'll come back to in a minute. We have the transmit message routine, which we'll come back to. Let's go all the way down to the main loop. Here in the main loop, you'll see that it collects information for the message, builds the message, does a transmit of the message, and then sleeps. So this occurs each time the user presses the user button. A new message is put together and transmitted. Now let's go look at the transmit routine. Okay, so the transmit receives the message, it starts listening on the radio, it then enters a while loop. And the while loop is going to check to see if the success count is less than 1, or if the number of failure count is less than the number of needed. And the number of needed is the number of retries we set, which is 3. And we stop listening, and we stop listening on the radio in order to send messages. So now we try to send the message. After we do, we wait briefly so that the other node can receive it. And then we start listening, and we're listening for the response from the main 0 computer. So we're going to calculate a start time and start watching the time as we wait to see if the radio receives any connections, any responses. If there is a response, then we read it. If not, we increment the number of failures by 1, and we loop back and try to send the message again. And we do this until the number of retries reaches 3. Let's say it does receive it though. In that case, it passes it on to this verify routine. Verify routine does a simple thing. It splits the data, which is the node number and the message. It takes the node number and builds the name of an address, and it compares it to the address of this computer. Okay, so in this case, node name has node plus 1, or node 1, and the address of this computer is node 1 that we define up above here, and we pass true back to this routine. If check node is true, then it increments the number of successes. If the number of successes is equal to 1, then this while loop is satisfied, and then until the user presses the user button again. Now let's look at the code for the main 0 microcontroller. The main microcontroller includes very similar code. It has the same imports, it has a pin definition section, it has a setup section for the radio. However, we only open up the RX pipe initially, and we're opening it on pipe 1. We start listening, because the purpose of this microcontroller is to receive data from nodes 1 and 2. So here's the response acknowledgement routine. Let's come back to that. Let's drop down to the main loop, and we'll see here that we're checking the radio to see if any communication is occurring. If it does, it receives it into a buffer, decodes it, splits it, and parses it to get the name. We print it out just so we have comfort on what's going on, and we pass the node name to the acknowledgement message. Okay, let's go look at that. Here in the acknowledgement message, we take the node number that we just passed, we combine it with node to form the address, just like main. We open up a transmission pipe for that address, and we stop listening, because as you recall, we can only transmit if we are no longer listening. We wait a slight delay, we build the response message, and then we send it. Here we're using the send start form of the method. The send start form of the method sends a message immediately without checking for any acknowledgement, because this is the acknowledgement. It waits briefly, and then it starts listening again and returns back down to the main loop. And it does this over and over again. So it's just basically waiting for a message, reads the message, parses the message, sends the acknowledgement to that specific node. And that's it. So in summary, setting NRF24L01 Plus for two-way communication requires considering the sequence. The receiving microcomputer appears to have the easier job, but then again, it still needs to store the incoming data. The effort to add a third microcontroller was easy, as we simply copied the node 1 code and changed the node number to node 2. Hopefully you now have a better understanding on controlling NRF24L01 Plus devices with MicroPython on STM32 microcontroller. In the next video, we will work on another external device, the PCA9685. Thank you.